We wanted to prototype as soon as possible, so the selection of particle board assembled with screws for the body allowed us to quickly and cheaply try new things. Tank treads were chosen due to their stability, ease of design, and ease of control at the cost of agility, because completion is our main goal and the speed of the run is secondary.
The robot captures the video and streams it to the base station. The base station opens the port and receives the data. When the data arrives, the base station puts it into the buffer. When the buffer fills, the video is streamed back to the driver.
We have the Raspberry Pi embedded on our robot, which hosts the server. For this, we chose to utilize the Python programming language as our language of choice.
We use the zero-tier software to assign static IP addresses to both the Raspberry Pi and the base station. For our server, we used a client list model for its ease of use.
So the robot receives commands via the server and decodes the message. This message is a composite of several different button states from the Xbox controller to control various portions of this robot. For example, you hit the right trigger, you pull the right trigger in, or you pull the left trigger in, and the robot will either go forward, this way, or reverse, that way. Hitting an A or a B button will cause an arm, which is in production, to raise or lower.
So for the electronics, everything's fed from these switch mode power supplies, which we made custom. They come in from the battery over here, and they are routed through to both of the PWM controllers and to the Pi itself. The motor supply is drawn from the battery itself because it's 12 volts, and we want to draw as much power as it needs. There's two PWM controllers. One of them is running at 50 hertz to keep the servo PWM at about 20 milliseconds, and the other here is 1600 hertz PWM for both the drive motors. The PWM for the 1600 hertz feeds directly to the motor controller, and the motor controller itself handles direction using a high or low call from the Pi. Everything's a bit of a mess right now because it's still a prototype, but we're working on a Pi hat that's going to sit right here on top of the Pi, as they do, and it will clean up a lot of these jumper wires.
For the server, we chose a clientless WebSocket model, and really we chose this because it's easy to use and Python has really nice built-in libraries already. It's easy to reconnect if it ever goes down. Really, we chose this server architecture because it was easy and reliable, and that's really what you want out of the server on a robot.
First up, when the robot is started up and executed, the server connects to its own IP and is starting to listen on a certain port for a client to connect to it. Once the client connects to it, it will start waiting for data to be sent over the WebSockets connection. But the thing is since it's an asynchronous process, it can be doing other things in addition to listening on that socket at the same time. So we could be updating other peripherals, updating what voltages should be outputted to the motors, the PWMs to the servos, all those different kind of things, all asynchronously.
This year I've worked on the control systems that will send data from the controller to the computer that we will use to send the data to the Pi that will run the robot. We'll be using an Xbox controller this year. We'll be reutilizing a Python file that has been implemented in previous years to give us a baseline for the controller, and then we will fine-tune what parts of the controller we'll use for certain aspects of the robot based on the driver's preferences, what motors or servos need to be controlled by the controller, and then we'll use all that data to put together an efficient and ergonomic layout for the controller.
Mostly I've done 3D modeling of parts for the robot, like for the claw, and 3D modeling the base and sides and tower to be laser cut. I haven't really used SolidWorks before, but it's nice having so many more like upperclassmen, experienced people ready to help me out. Modeling the hand has been a lot of fun to ready to be 3D print. It's difficult to get all the gears to mesh together, but we got it done.
So I've worked on selecting out a battery and doing the calculations for the lights, LED lights at the front of the robot to guide us through the tunnel. So with the lights, I had to calculate and test the voltage drop of the LEDs because they were not exactly the same as what the data sheet was. And then using that and combining that with the current that we could draw, I figured out what resistor we need to put with those. With the battery, I basically picked out like voltage that'll help drive all the components of our robot and make sure we supply enough current.
My specific project for this robot has been designing a custom PCB and casing for the LED headlight. More generally, I'm also helping out working on the electrical layout and the wiring of the robot.
I worked on the static and dynamic parts of the robot. By that I mean securing the tower of the robot correctly, so with cables and stuff, make sure it doesn't break, and then it stays stable the entire time. And I've also worked on the design of the body, making sure it functions and can support the weight of the robot.
Mostly I've been involved in selecting the drive motors and also the servo motors that will control the payload arm. I've also assembled the chassis of the robot. I think what I enjoy the most is just watching everything come together. When we laser cut the parts for the chassis, that was one of the most exciting moments for me. I really enjoyed witnessing that.
Oh, I think the team has worked together spectacularly this year, and this is because I think we're all young, we're all somewhat inexperienced, but we're all on the same page in that we're all here to learn. Everyone is just trying to learn how to build a robot, they're all trying to become a better engineer, and they're all trying to make friends. And so when everyone is headed in the same direction, it's really easy to be a leader. And I think our team is headed in a great direction.
So last year in competition, our bot got flipped over and we weren't very durable. So we knew this year going in that we would want to be flippable, be more durable, and we liked the idea of a vertical spinner. So we put all those things together and came up for the design on our bot, which we voted on, and there it is.
So I've done this competition for about 5 years, and I still learn things every day from it, especially in the build phase. Something that has definitely surprised me and continues to surprise me is just how much time is poured into the build phase of the robot. You always forget that each part that you're designing takes quite a few man hours just to create and manufacture, and then you have to edit that piece to make it fit within the robot, because things don't always work out the way you want them to when you're taking it from a design phase to a build phase.
I'd like to talk about how teams get started up and some few key points that you'll need to get going. So most importantly is make sure you read the manual. You need to know what's going on, and you need to know how things work at these competitions. there is a bit more going into it than just simply designing something and putting it into an arena to fight. It also helps you to figure out how other teams may play the game, because these restrictions, they will make you have to think in specific ways. Another key point is that once you start getting an idea of what you need to do and you start building on a system, make sure you work on the drive system and building a base that you can practice driving on. Because even a great bot can fail if you have absolutely no experience in what you're doing.
I am here to talk to you about what we would do differently next year and some of the errors we've made. And so mainly what we would do differently next year is better version control for our SolidWorks model, and that would allow us to have better prototyping and kind of see where we've gone, and if we need to go back, we can. It's easy to revert changes.
So some of the strengths of a robot is the armor design. The back is wedge shaped, so it's going to be hard to get underneath us, and on top of that, we'll be able to wedge underneath other bots. And then the weapon is going to be very powerful. It's going to be driven by a very large 1/5 scale motor, so it's going to have lots of power. The weapon itself is around 5 pounds, so it's going to have a lot of inertia when it's spinning. Our drive system is very effective. It's brushless DC motor, so we're going to have plenty of power when it comes to actually moving. And the electrical system just overall is going to be a very powerful electrical system this year.
And I'm going to talk about the weaknesses of our robot. Personally, if I was going against our own robot, I would try to attack through the sides. Reason being is that at the front it has the weapon, obviously. At the back it's wedge shaped, so it would be very difficult to attack through that side. So the best bet would be to try to attack through the sides.
So I'm going to talk about how work is divided on our team. So towards the beginning of the year, I try to get everyone's majors to see what they have experience in, and then I try to task them to things related to their major, such as Kyle Bannon. He's a mechanical engineer, has a lot of work with SolidWorks, so he is currently heading up the SolidWorks section. There's a little separate team that does SolidWorks, so he's heading that up. Other mechanical engineers are kind of working under him, just designing everything to do with the robot. Myself am an electrical engineer. Bradley Snow and Omar are also electrical engineers, so they kind of work under me on electrical stuff, such as soldering, connecting components, stuff like that. Then we have Jeffrey, who does like our documentation. So basically, I just try to match jobs to people who kind of want to do those jobs and have some expertise in those.
Something we used prominently was SolidWorks. We used it to design pretty much every aspect of the bot, and most of our time was spent in SolidWorks. I feel my experience using SolidWorks will really help me in my future as a mechanical engineer.
When we were coming up with our launcher idea, we had a few ideas to go off of. One of them was using compressed air to be able to launch the ball, or we had some kind of kinetic launcher idea. It was a very basic kinetic launcher idea, and we didn't really know what we were going to do with it. So we got to talking more about the compressed air idea, because that was our more solid idea, and we realized that's really hard to do. So, and after doing some research and learning about different kinds of kinetic launchers, we decided to prototype an idea that we had that involved using rubber bands and a sliding sled to hit the ping pong ball and launch it. And after creating the prototype for that, we realized, wow, this works pretty well.
We stuck with the same wheel design with 4 independent 12-volt DC motors. We were really impressed with its precision and maneuverability from last year. This year we went with a little bit smaller wheels because we were concerned about the height of the shooting mechanism meeting the height of the bridge. This year I found some nice wheels from Polo Lou. They actually had a compression fitting in the middle, which fit tightly around the shafts. That was a problem from last year, where the wheel hubs didn't really fit tightly enough on the shaft of the motor, so there was some slipping due to the weight of the robot.
The thing that surprised me most about building the robot this year was how portable our code from last year was. I was impressed about how well designed the code was, in that we could reuse and really just upgrade a lot of the code from last year.
So the Pi communicates with the servos using an I2C protocol, and then it uses I2C protocol to talk to a motor driver. And the motor driver is then able to take the I2C signal sent from the Pi and translate it into a PWM signal.
So I have worked on the power delivery to the robot. This involved choosing the battery and making sure that the systems are powered properly within the robot. The battery we chose was an 11.1 volt lithium-ion battery. It provides plenty of power for everything that we need.
Before we started working on the robot, I was really surprised by how many new members that we got. Because last year, the mechanical team was just me and one other person. But this year we got 3 or 4 new members, and they've all been really productive, and they've been coming to the meetings. It's been great.
One of my favorite parts about being on the robotics team is being able to work with people in other engineering majors. I, as a mechanical engineer, get exposed to things like SolidWorks, things like that, but I don't get to work with circuits as much, and being able to work with the electrical team and the programming team to learn new things about Python and how to use motor controllers was really cool to me, because it's something I don't have as much access to during class.
The thing that surprised me the most this season about working on the robot was probably just how well we work together as a team. With robotics, we come from all different kinds of disciplines, whether it be mechanical engineering, electrical engineering, even industrial engineering or biochemistry. It's just amazing how a team of all these individuals can come together and create something that's really awesome and compete in a robotics competition.
The biggest obstacle that we're going to have to overcome with the robot this year is the bridge, but I'm really not that worried. We'll get over it.